Welcome to Multidisciplinary Design Optimization on Optimization Algorithms. So this is the table of contents of last lecture, where we covered the first basic gradient-based optimization algorithms like steepest descent, conjugate gradient method, modified Newton's method, quasi-Newton's method, and we got in first contact with methods to treat constraint optimization problems by turning them into unconstrained optimization problems using penalty and barrier functions. And in our big overview, you can see that we covered this part. We also covered particular one-dimensional zeroth order optimization algorithms for the line search. And for constraint problems, we covered barrier and penalty methods and one dual method, the so-called augmented Lagrange method. Today, we will mostly focus on Lagrange methods, so-called sequential linear programming and sequential quadratic programming, and then we will briefly discuss evolutionary algorithms. So this is the table of contents for today. We start with linear programming, then show how this can be embedded into sequential linear programming. Then we discuss quadratic programming and put that into what we call sequential quadratic programming, and then briefly talk about evolutionary algorithms. And we will get started now with linear programming. So first of all, this term here is maybe a little confusing because we are not yet writing computer programs, but what we are talking about is something that you can use to write computer programs. So linear programming is a collection of methods, you could say, to solve linear optimization problems. So when people talk about a linear programming problem, what they mean is an optimization problem that is linear. Linear programming, strictly speaking, covers only linear optimization problems, but they are very important because they will serve as module for sequential linear programming, what we will cover in the next chapter, which can also be applied to nonlinear problems. So at first, consider a linear optimization problem of this structure. So the objective function is a vector times the vector of design variables plus a constant. And then we look at this optimization problem where we minimize the objective function with respect to its arguments, subject to an equality constraint using the equality constraint function h, which is also linear. So it's a matrix A times x plus b, and it is set to be 0. And a inequality constraint function, which is equal to a C matrix times x plus a vector d, which is supposed to be less or equal to 0, and with our bounds on the design space. So we know that for this type of problem, an optimal solution is always on the boundary. So that means the solution is either a vertex, that means it's the intersection of two constraints, and then there is only one solution. Or if one constraint runs parallelly to the objective, to the to the contour line of the objective function, then you have an infinite number of solutions. So in this case, the problem would not be well posed. Also, if you have contradicting constraints, then you may end up with no solution, which also means that your problem is ill-posed. There are several different algorithms for linear programming, and in this lecture we will only cover one representative of them, but it is an important one. It's called the Simplex Algorithm, developed by George Danzig, and it is a very nice algorithm with a very intuitive underlying idea. So since you know that for a linear optimization problem, the optimum has to be, if it's unique, on a vertex, then you can just systematically check vertices for optimality. And this is also what this algorithm is based on. You start on one vertex, and then you proceed to the next vertex that improves the value of your objective function. And how you can do that using an algorithm, I will show you in a second. This algorithm exists also in MATLAB, and the code word for this would be linproc. So we will restrict ourselves to an optimization problem using inequality constraints, but it will be very obvious how you can treat equality constraints the same way. But for simplicity now, let's just consider this problem. So we want to minimize the objective function, which is linear, subject to an inequality constraint, and also this is a particular convention that we will adopt. We will restrict our design space such that design variables have to be greater or equal to 0. But there is no technical restriction on the right-hand side of the design space. That needs to be taken care of by the inequality constraints. And actually, if you would like to restrict your design space, you would just formally express that as an inequality constraint here using G. So let's start with a simple overview. We're going to distinguish two phases. So there's the initial phase, where our iteration index assumes the value of 0. And then there is the iteration phase, where the index will adopt values which are equal or greater than 0. And just one comment on this notation. In last lecture, we used a notation that was slightly different, and to avoid confusion, we updated this notation. So you may remember that in the lecture notes there was, in this column here, it said that k is to assume the value k plus 1, and we had it in this part. This is now moved to the to this section because technically there is no difference between assigning design variables vectors a value and this index a value. So whenever there is an assignment of values, we say set, and we name the variable, and then there's an equal sign, and then there is we state the value that this variable is to assume. There will be an update of lecture notes 5a, where we corrected this, but only this. So if you made notes already, if you took notes in your printouts, you don't need to download version number 2 of this update. But if you haven't done that yet, please use version number 2 because there we adopted this kind of notation for algorithms. So, in the beginning, we need to set up the optimization problem such that we can work on it. And the first step for this will be to introduce a design space, to expand the design space using so-called slack variables to turn inequality constraints into equality constraints. And this is the way it is done. So you can turn this optimization problem here on the left-hand side into an equivalent optimization problem where we replaced this inequality constraint by an inequality constraint using this new function g hat, which depends on a extended design variable vector x hat. And that design variable vector now includes slack variables that also have to be greater or equal to 0. And if this is the case, then a solution for this problem will also be a solution for the original problem. If constraints are active, then the associated slack variables will assume the value of 0. If they're not active, then they will be larger than 0. Then we set up a so-called Simplex Tableau. And how this is done is shown here. So an example of a Simplex Tableau in canonical form is shown here. What is a Simplex Tableau? A Simplex Tableau is essentially a set of linear equations that you can use to compute vertex positions. The so-called canonical form includes always m, the number of inequality constraints, m unit vectors. So in this particular examples we have, actually in the example that will be shown later, we will have 3 unit vectors. But here it's general. There are m unit vectors, so just as many inequality constraint functions you will have unit vectors. And those variables that are associated with those unit vectors will be called basic variables. So basic variables will change, and for example, xd can turn into a basic variable, but if it is a basic variable, it will also have a unit vector here. How this is done, I will show you in a second. But now think of this as a scheme where you have just as many unit vectors as you have inequality constraints, and then you adopt the convention that whenever you have a non-basic variable, it assumes the value 0, then you can use this part to solve for values of these remaining variables, because you have an m times m matrix here, and you have the right-hand side vector, which will change during the course of the execution of this algorithm. So in the beginning, you make all your slack variables basic variables. You write down unit vectors here, and you write down your C matrix here underneath your design variables. And the right-hand side will assume minus d vector values. And this represents, if you solve this system of equations for assuming that these variables here are all 0, what you would get are the values for the slack variables. And, well, since the non-basic variables are 0, all your x values are 0, saying that you are in this corner of your design space at the origin. If you have a problem that where this point is not feasible because there is a constraint running like this, for example, then you need to transform your problem into one where the origin is included. But this can be done by appropriate coordinate transformation. So you can always create a vertex at the origin by changing your problem appropriately. So now let's assume that you are in this state, that your initial x vector is 0, and your slack variables assume the negative d values. Then let's look at the next step. So now you need to change basic variables, and you do that by first choosing a so-called entering basic variable and a leaving basic variable. Let's look at an example to see how this is done. So this example here is one with 2 design variables and 3 constraints, 3 inequality constraints. And this translates to this simplex tableau here. So for example, you can see that the coefficient of constraint number 1 for design variable 1 is simply 1. Okay? And you can see that the right-hand side is negative d vector component number 1. We have 3 constraints, therefore we have 3 lines in our simplex tableau. And since we have 3 constraints, we also have 3 slack variables. And in the beginning, all slack variables are basic variables with associated unit vectors underneath. And now if you solved this system of equations with the non-basic variables being 0, then you can see that your slack variable number 1 will be 18, slack variable number 2 will be 20, and slack variable number 3 will be 8. Well, but we are not very happy at this position here, and the fact that there must be better positions can be observed by looking at this line here. So in this line, we can see that the coefficient of the objective function for the first design variable is negative, saying that if you go down x1, going down this coordinate direction, you will decrease the value of your objective function, which is nice because we want to minimize the objective function. But going down x2 is even better because apparently it is much steeper going down x2. So what we would like is we would like to explore the next vertex going down x2. How do we get there? Well, we do that by choosing x2 to be a so-called entering basic variable. This is the one that we want to make a new basic variable. But in order to be able to do this, we need to remove one of these basic variables, which is like saying, let's not make a slack variable a basic variable, but instead a non-basic variable, which means that the slack variable will assume the value of 0, which again means that we will activate this constraint. So, and which constraint should we activate? Well, going down x2, you wouldn't want to activate this constraint, for example, or this constraint, or this constraint. The one you would like to activate is the one that will become active first. And how to choose the one that becomes active first, this is explained by thinking about what would be your leaving basic variable on the next slide. The leaving basic variable is to be chosen such that going down the entering basic variable will hit a constraint that is associated with the slack variable, which is to be chosen as the leaving basic variable. Okay? And how do you choose that constraint? Or how do you choose that row associated with the constraint? In other words, how to choose the index j that will tell you what constraint will be activated. Just look at this diagram here. You can think of this diagram as a section of this plot where you go down x2, and here you can see how the different constraint functions will behave. You have a negative right-hand side here because this is the right-hand side of the system of equations. So if you subtracted the right-hand side, then you would have the function itself. Yeah? So then you would have coefficient times design variable minus right-hand side equals 0, and you're looking now for the root. So the first time that your inequality constraint function becomes 0. And which constraint function will become 0 first is a question of what the ratio of the right-hand side and the associated coefficient will be. So we want to choose the row j with the lowest ratio of right-hand side j divided by c tilde ji, where I denotes the entering basic variable, and cji tilde is the update of cji. What do I mean by update? Well, update refers to the fact that this operation that we're currently doing will change this tableau, and the step that we are currently carrying out will have to be repeated. And you will always use the values of the current tableau to carry out that step. Yeah? So it won't be the values of the original C matrix anymore. It will be something else. It will be the result of your previous steps. So once you chose that row, then you can identify the leaving basic variable simply by the variable that has a 1 in that line j. So in this case, it would be the slack variable 3, which is connected with constraint number 3. And this is the one that will become active first. Okay, so now you have your entering basic variable, x2, and your leaving basic variable, which is slack variable number 3. And now you can perform the switch. And this is done by a so-called Gauss Jordan elimination process. And what you do is you make your column of the entering basic variable, you make that, you turn this into a unit vector, the same unit vector that you had here. And you do that by adding rows or multiple of rows such that this entry will become 0 and this entry will become 0, but you need to add entire rows. And this is like changing your coordinate system, and that will allow you to move towards the next vertex. So after you carried out this elimination process, you have a unit vector below x2, and you have something different below the slack variable number 3, which is now a non-basic variable. So the non-basic variable now assumes the value of 0, so we're here, meaning G3 is active, and x2 is different from 0. Well, in fact, it turns out that x2 evaluates as 8. So in the next step, you check whether you are at the optimum. In this case, you don't use classical convergence criteria. You verify optimality differently. So if all of your coefficients of your bottom row associated with your function value f are greater than 0, then you know it's only going uphill if you move away from that vertex. And that means you're done. And also, due to the way this tableau was set up, you can identify the function value of your objective function as the negative value of the right-hand side, 760. And then you're done and you found your optimum. Let's continue with sequential linear programming. So in sequential linear programming, you try to solve nonlinear optimization problems by a sequence of linear approximations of your problem. So what do I mean by linear approximations? So if you think of two constraint functions, g1 and g2, and your current point of interest, let's say, is right here, then you would replace your nonlinear constraint functions by linear constraint functions and just solve an optimization problem using these linear constraint functions. In 2 dimensions, this is shown here, so imagine you're at this point. Then the linear approximation of this constraint function g2 would look like this. The approximation of your constraint function g1 may look like this, for example. So, and then ending up solving this optimization problem would have you end up at this point rather than this point, for example. And since this is not an accurate solution, you would have to iterate. Let's look at the algorithm for sequential linear programming. At first, you select a start vector and so-called move limits. The start vector can actually be chosen arbitrarily. It may even be non-feasible. So you can linearize your problem around at a non-feasible point, and then enter the linear programming algorithm that will construct or that will find the feasible domain. Yeah? So this is something you do not need to take care of. What you need to take care of, though, and that's important, is to choose so-called move limits. The algorithm will find a candidate solution for each iteration step, and then we'll have to linearize your problem again, and then run a linear optimization again. And for this process to converge, it's important that you don't move too far away from your current design, and you ensure that by choosing move limits that will just prevent your solution from jumping back and forth. And one way to choose move limits, there are different ways, is that you essentially bound your next design candidate by these two limits. So it would be a factor 1 minus theta times your current design, and the other bound would be 1 plus theta times your current design. And you would have to choose your move limits between 0 and 1. So if you chose it to be 0, for example, you'd be extremely tight. Of course, you wouldn't want to do that. And if you chose it 1, then you would give more space and would allow the algorithm to make large iteration steps. Which value to choose depends strongly on the problem that you want to solve, and there is no general rule of thumb for that. So let's look at the linearization of your optimization problem. For linearization, we will be using gradients, and I'd like to define what a gradient is here in this context. So think of v as a vector or a scalar. Then we call the gradient either dv to dx or nabla v. And we want the gradient to be such that you can multiply it with the x differential, which is a column vector. Therefore, the expression that is in front of your column vector needs to be a row vector. Since we want the gradient itself to be also a column vector, we need to transpose it. Okay, so the definition of the gradient can be seen here. We want nabla v to be such that it is a column vector, and then we need to transpose it in order to multiply it to a differential. And therefore, if we do a Taylor series expansion, we will have to write that the approximated objective function f at a position x is the function f at the reference point plus the gradient transpose evaluated at the reference point times delta xk. And delta xk is defined as the x vector minus the reference point. Okay. Similarly, we do this with the equality constraint function and inequality constraint function. So once this is done, we can set up the linearized optimization problem as this. And now our design variable will be x. So h of xk is a constant. And this expression here, which is a matrix, will also be constant, times delta x, which includes the optimization variable x. You want to include explicitly the move limit as a constraint on your x. And now you can solve a linear optimization subproblem, compute the solution, and then adapt move limits for the next step, because you want to make them smaller and smaller once you go on with your iteration. Then you set, you increase your iteration index, and you check whether you end up with a feasible point. If you didn't, you have to go back to 2. And if you did, you can check convergence. If you did converge, then you're done. So you want to make your move limits increasingly smaller. And as a heuristic or a rule of thumb value, you can use 0.7 as the ratio of the next move limit and the current move limit. But that's also something that you would have to choose according to your problem that you're trying to solve. So this I already mentioned. If your new design point is not feasible, you would have to repeat the second step and reduce move limits. If your new point is feasible in the original problem, then you do your conversion test. And after that, you may nevertheless repeat the second step, or you're done. There is an alternative algorithm where you do not jump directly to the solution of your linear optimization problem, but you use it only to define a search direction, and then you conduct a line search. And that line search could be enriched with a penalty function using the constraints of your original problem, and of course also your move limits. So this way you would refer to, or you would use more information of your original nonlinear problem and possibly improve the result, but then of course you have extra computational effort to perform the line search. Some final remarks on sequential linear programming. Sequential linear programming is very powerful for weakly nonlinear optimization problems. It can be very fast. However, for nonlinear problems, it doesn't work so well, and other methods are recommended, like SQP, which we'll be covering in the next 2 chapters. And also you need to choose your move limits wisely for good performance. And for that, well, we cannot make a general recommendation. That is something that is very problem specific, and you may have to play around until you find a good value that controls the evolution of your move limits. Let's continue with chapter 5.9 on quadratic programming. Like linear programming, quadratic programming is a collection of solution methods, but this time it is to solve quadratic optimization problems, and it will also serve as a module for a larger framework that can be applied to nonlinear problems, which is called sequential quadratic programming, or SQP. So the most general quadratic optimization problem can be written like this. So you take some Q matrix, which is quadratic, it doesn't have to be symmetric necessarily, and multiply it twice by the design vector, plus a constant vector times x, plus a constant z, and you subject it to linear equality and inequality constraints and some bounds on your design space. And then you could have something like this. So you can see contour-lines of your objective function and linear inequality constraints and linear equality constraints, just as an example. So there are several techniques to solve quadratic programming problems. However, we will only address one or some of them. And it's important to distinguish between two different modes. The first mode is without inequality constraints, and that's the simpler mode, for which you can obtain a solution by just solving the stationarity conditions for the Lagrangian. It gets a little more complicated if you have inequality constraints, because the KKT conditions, they tell you nicely what conditions need to be satisfied for optimality, but you don't know yet for which candidate designs, and you need to find them. And in order to find them, you need one strategy to adopt is the so-called active set strategy that will help you to identify these points. And the active set strategy relies on dividing your set of constraints into an active set of inequality constraints and into an inactive set of inequality constraints. And those active constraints, those active inequality constraints, you simply treat as equality constraints. And then you solve for the solution of one iteration step, and then you need to update your active set, because by moving in the design space, you may actually run into inequality constraints. Formally, the set of active inequality constraints is represented by an index set, JG, and it could look like this. So JG being the set with two elements, 1 and 4, means that constraints 1 and 4 are active and all the others are not. So this is the overview over the quadratic programming algorithm that relies on an active set strategy. And we start by looking at how to select a start vector. This time you do need a feasible start vector, because the algorithm that we are talking about here requires a feasible design. And finding feasible start vectors can sometimes be complicated, and is done by algorithms that we do not cover here. Yeah, so typically vertices that are defined by intersections of your inequality constraint functions are good candidates. What you need in the very beginning is that you have a design for which you know which constraints are active and which ones are not active, because you want to start with a well-defined active set. In the next step, you want to solve for the search direction by solving the Lagrange-Newton equations for active constraints. And for this, we need to transform the original quadratic programming problem with inequality constraints into one with equality constraints only. And we can do that by replacing the inequality constraints by equality constraints for those constraints that are active and ignoring those inequality constraints that are not active. So this is the underlying idea of the active set strategy, but we need to carefully update the information, what constraints are active and what constraints are not active. For those constraints that are active, we can solve the stationarity conditions, the so-called KKT conditions, for quadratic problems. And we do that by looking at the Lagrangian function and replacing the objective function and the constraint functions by the expressions of the problem statement. And then take first order derivatives with respect to the design variables, the Lagrange multipliers, and set these expressions to be equal 0. Then we write that in a matrix notation like this. And this is something we could solve already, but we would like to rewrite that for an increment or a search direction sk. And therefore we do a little bit of algebra and replace xk plus 1 by this. And rewrite the right-hand side and then obtain a formula for the search direction and an update of the Lagrange multipliers, which looks like this. Then there are 4 cases to distinguish. One of them where we have a search direction which is unequal to 0, and the constraints of the original problem are satisfied. There is a case when the search direction is unequal to 0 and the constraints of the original function are violated. Then there's the case where the search direction actually evaluates a 0 and the smallest Lagrange multiplier evaluates as less than 0, meaning the necessary condition of optimality is violated, so it is not an optimum. And then there is the case where the search direction evaluates a 0 and the smallest Lagrange multiplier evaluates as greater than 0, which means the necessary conditions for optimality are satisfied and we can stop. Let's look into these 4 cases again in more detail. So, case number 1, the new design, or well, first of all, the search direction is not equal to 0, and the candidate design satisfies the inequality constraints. You have a feasible design, and you can proceed to the next iteration step. You know you're not optimal because if you were, then S would be 0. Case number 2. There's a search direction which is unequal to 0, and you're not feasible. So this is the scenario where you need to activate a constraint that hasn't been active before. So what you do in this case is that you keep that search direction, but you compute a step size for the constraint that is violated most. So there could be several constraints violated, but you want to start with the one that yields the largest value of the constraint function. So you add that constraint to the active set and then compute a step size using a linear constraint function that looks like this. Cj vector, which is a row of your C matrix that was used to formulate the inequality constraints, times your current design plus an unknown step size times the search direction that you know, that has to evaluate as minus dj for the constraint to become active. And this lets you compute explicitly the step size alpha k that you need to progress exactly to that point where your inequality constraint becomes active. And then you go on. Case number 3. The search direction is 0, saying that you're not making progress. So that's the first hint that you could be at an optimum. But unfortunately, the Lagrange multipliers, the smallest Lagrange multiplier is negative. Well, that means that you have active constraints, but going away from them would improve your results. So what you would do is you would remove this constraint and from the active set, and then start over with a new iteration. Case number 4. The search direction is 0, but this time your Lagrange multipliers are all positive. Well, in this case, you know that the necessary conditions for optimality are satisfied, and you're done. Now let's apply this to sequential quadratic programming. Sequential quadratic programming, or SQP, is used to solve nonlinear optimization problems by a sequence of quadratic optimization problems. And well, there are again many ways to formulate the quadratic subproblem. We will show you one of them. In MATLAB, you can access the underlying algorithm by the so-called fmincon, which is quite famous procedure, and activating active set algorithm, the active set algorithm flag in the optimization options. This is the overview over the algorithm. The start vector will be selected as a feasible start vector, like for the QP problem, to set up the active set. Then you derive a quadratic subproblem. The quadratic subproblem is the linearized version of the stationarity conditions for an increment xk plus 1. So if you take the Lagrangian function, and we formulate it here only using equality constraints, but you can think of this as the equality constraints that also include the active inequality constraints, which can be treated here as equality constraints. And then we look at the necessary condition for optimality, that the Lagrangian function becomes stationary, meaning that the gradient vanishes. Okay, and the gradient of the Lagrangian function we expand as a first order Taylor series, which means that we take the Lagrangian function evaluated at xk plus the gradient of the Lagrangian function evaluated at xk multiplied by an increment vector, delta x and delta lambda, to approximate the gradient of the Lagrangian function at xk plus 1. And then again we set that equal to 0, and this here will give us an equation to solve for our increments. This here is the same expression, but with the second order derivatives of the Lagrangian function explicitly written for x and the Lagrange multipliers, and then filled in with the definition of the Lagrangian function. So here's the second order derivative of the objective function plus the Lagrange multipliers multiplied by second order derivative of the equality constraint function or functions, and the first order gradient of the equality constraint functions transposed, and also on this side not transposed, multiplied by the increments equals the expressions for the first order derivative, derivatives of the Lagrangian. So there are two more things to do to come up with the final version. One of them is that we replace the increment by the search direction. That's just renaming, but that's meant to remind us that we will not go to the next design, to the next candidate design in one step, but we at first only specify a direction, and then we will conduct the line search. And the second thing we want to do is we want to replace delta lambda here by lambda k plus 1, and this is to eliminate lambda k from the right hand side, which came from the gradient of the Lagrangian function. Yeah, but by replacing delta lambda by lambda k plus 1, this here will go away. And we come up with something that looks very similar to the quadratic problem that we solved in the previous chapter. So this here can be treated as the result of a quadratic optimization problem that looks like this, with a Q matrix and an SK vector that you want to solve for, and a vector, a constant vector, which is here the gradient of the objective function evaluated at xk plus a constant. And so this here is the substitute quadratic subproblem that we were looking for. So please note that the Q matrix is not the Hessian of the objective function, what one might think. Yeah, so you could think of the quadratic subproblem being the problem that you obtain when you approximate f as a second order Taylor series, and then just take Q as the Hessian, but that's not the case. What we are doing is we're approximating the Lagrangian function, and therefore we also have these expressions in the Q matrix. So remember the inequality constraints that we did not explicitly treat here. They are either active, then they are part of the equality constraints, or they're inactive, then they're ignored. And the bookkeeping of what constraints are active and which constraints are not active is done in an outer loop. So that's not part of the step here. With this quadratic subproblem derived, now you can solve for the search direction and a corresponding Lagrange multiplier lambda k plus 1, and also mu k plus 1 by doing the bookkeeping that we introduced for quadratic programming when we checked whether active constraints are violated or not, and updates were made accordingly. So after you got this search direction and the new Lagrange multipliers, you need to compute the step size to come up with the new candidate design. And this is done with a so-called merit function that includes the original objective function and also the constraint functions of your original problem, the equality constraint functions and the inequality constraint functions, because there is no need to use the substitute problem right now. So here on the line along your search direction, you will look for an optimal value of alpha that minimizes this merit function. And you could do that by using the methods that we introduced in the previous lecture. Bracketing, sectioning, and polynomial substitute models for the estimation of an optimum. Let us conclude with some final remarks on SQP. SQP is one of the most widely used algorithms in engineering. It is very powerful, and it has, for a broad range of problems, a good balance of numerical performance and applicability. So it can be applied to nonlinear problems that are not too nasty, and it produces a result in a reasonable time. What we discussed in this lecture is also combined with what we discussed last lecture. So we want to avoid computing second-order derivatives and inverting the resulting matrices. So what you want to do instead is use quasi-Newton methods that rely on approximating second-order derivative information using gradients. So as we discussed for the BFGS method. Also, scaling can become an issue, so you do not want problems where design variables are on extremely different scales. So let's say one on the order of 10 to the minus 10 and the other one on the order of 10 to the plus 10. In this case, you want to rescale your problem. This can be done either using variable scaling, or what is also recommended to do is that you normalize your design variables with respect to the design space. So in that case, you typically get a reasonably scaled problem. So we finished our section on Lagrange methods. And for this lecture, there are only evolutionary algorithms left that our research assistant, Lukas Krischer, will explain to you.
Hi everyone, and welcome to the last part of lecture 6, Evolutionary Algorithms. Evolutionary algorithms are zero-order methods, so they don't rely on gradient information, but rather on some heuristics derived by nature. Before we go into detail, I just want to mention that this is a huge field and there are whole lectures on evolutionary algorithms. Therefore, we just want to give you an introduction to the field, that you know the basic concepts, and even this might help you to implement algorithms if needed. So, evolutionary algorithms are based on the principles of biological evolution and genetics. That's what I mentioned before. So basically there is a population of designs. So there's not only one design variable vector as we have it in the deterministic approaches, but a set of design variable vectors. And those are iteratively modified in order to improve the results, so to produce new generations. And this, as I mentioned, is based on biological principles, so they are called genes. So these genes, so the information of each individual, which are the design variables, are passed to the next generation. There exist a lot of different approaches. We will cover 3 of those in this lecture. So the first one are genetic algorithms. Then we will talk about an algorithm that is called differential evolution, and finally a particle swarm optimization. And lastly, there are 4 basic operations within evolutionary algorithms: recombination, mutation, evaluation, and selection. Recombination is also sometimes called crossover. So here the characteristics of parent individuals are combined in a way to create new children with new information. Mutation alters the properties itself. So you have one individual with its design variables, and those are changed according to some heuristic. Then evaluation itself is just to evaluate the fitness, which is mostly equivalent to the objective function value. So the design variables, the genes, or chromosomes are evaluated with respect to the objective function or fitness function, and this is called evaluation. And finally, the selection process. So here, out of a population, so a set of design variable vectors, a new subset is defined for the new iteration. Now let's have a look at the general overview of evolutionary algorithms. We start with the initialization phase, and here I want again press that the difference is we now have a set of design variable vectors. So here with the indices a to n, so we have a population size of n. So it's a set of design variable vectors x, which are initialized, and afterwards we see the 4 basic operations. So it's mutation, recombination or crossover, evaluation or selection. Note that this order is not fixed, so it might change, and also sometimes those operations are kind of merged. So you not have always explicitly an evaluation, sometimes it's also part of the mutation or recombination operation as well. And after each operation, we can still do a convergence test on the whole population, and if those criteria are met, we can also stop the iteration. Our first evolutionary algorithm is the genetic algorithm. It was introduced by Holland in 1975. It's a population-based stochastic optimizer mimicking the evolution. So in our other categorizations, it is a stochastic optimizer, and it also has global convergence characteristics. Especially for the GA, there are a lot of different approaches how to carry this algorithm out. We will follow the basic idea for real value design points, and here you also see the nature-like approach. So we have chromosome-like structures in binary arrays, which we will also show in the next slides. The first phase is the initialization phase. So we start to create random sets of chromosomes with random sampling methods or Monte Carlo sampling. And here often real valued variables are discretized to genes for chromosomes. And how it is carried out, you can see here. So for instance, this is one individual. So individual, this is a set of, so this is a design variable vector here with 1, 15, 12, and 3. And what you do is now you convert it to the binary system. So here's now the binary representation of those numbers. And these are our chromosomes. The variables, of course, are then limited to the bit representation numbers. So for 8 bits, we have 256 discrete values that we can realize. And the quality of the chromosomes is then evaluated by so-called fitness functions. So in the field of evolutionary algorithms, it's often called fitness functions. They can be the same as the objective function that we already know from the deterministic approaches, but sometimes also the objective function is additionally changed to improve the convergence behavior of evolutionary algorithms. Then we go into the iteration. So the first part is the selection of the parents. And here we see also that in the selection part there is evaluation taking place. So the pairs of individuals, so these are the parents, are selected based on the evaluation of their fitness scores. If you have a better fitness score, so a lower objective function value, the chances are higher that you are taken as a parent. So one approach of many is the roulette wheel selection. So I think it's pretty straightforward. So the probability of being selected is directly proportional for your fitness function value. So you can think about it as a roulette wheel where you have a higher chance of getting selected if your fitness function is better or your objective function value is smaller. But besides that, there are also some other approaches, so not only proportional to the fitness functions, but also elitist approaches where you just only select the best fitness function values. It's always a trade-off between exploitation and exploration. And the reason why it's only called selection is that there are also other methods that just, for instance, they are randomly taking values of other individuals just in order to ensure the exploration of the whole design space. So that's why it's selection, not evaluation as a separate step here. After the selection process, we go next to the crossover or recombination operation. So for the crossover operation, there are different ways of carrying it out. So for the single point crossover, here we have one example for it. So we have two parents. So this is one binary representation of one design variable, and this is another binary representation of a design variable. So this is 184, and this is 193. And by a single point crossover operation, we have a weighting factor R, which is defining the position where we do the crossover. So the crossover position is here and here now. And then we just do the crossover operation and we change the genes of the chromosomes respectively. So these genes are going there for this chromosome and the other way around. And this is the way how we create new children here. A different way of doing it is a uniform crossover. So here each binary gene is chosen from one parent. So you can see that those genes of this chromosome of parent 1 and those genes of parent 2 are then just changed respectively for the children. So the others remain the same. So you see 1 to 1 and so on, 0, 0, but then from parent 2 the others are changed here and marked with green and here with red respectively. After the crossover operation, we go on with the mutation first. The difference between mutation and crossover is that now there's not a set of parents that are involved, but only one parent is mutated. And here's also the definition. So minor random tweaks to the chromosomes of the parents. And there are different operators for that. So here just some examples, for instance, the bit flip. So in the bit flip for binary representation of chromosomes, you just flip the corresponding bit either from 1 to 0 or from 0 to 1 for a specific amount of genes. For the swap, you just swap two genes in the chromosomes accordingly. So the 1 gets to the 0 and the 0 to the 1 respectively. And the last example here is the inversion. So in the inversion, the order of the single binary representations of the chromosomes are changed. So here we go from the left to the right. So it's 1, 0, 1, 0, 0. And then for the inversion, so for the child, it's the other way around. So we go from the right to the left. So these are just examples for mutation. And after the mutation, we have again a selection process for the next generation now. And there are different ways of doing it. So these are just examples. Again, there are multiple ways of doing it. Here we have as one categorization the age-based and fitness-based approaches. The fitness-based approach, so here we do evaluate the individuals, both parents or children. Sometimes only parents are evaluated or children's, but anyway, so you evaluate them and according to a specific heuristic, you choose them for the next population based on their fitness values or objective function values respectively. In an age-based approach, it's different. So here you do not evaluate, but you're just defining, okay, all individuals stay in the population for a specific time duration and afterwards they are neglected. After having discussed the genetic algorithms, we now go on to the differential evolution. So here you see the general overview over the differential evolution algorithm. It was introduced by Storn and Price in 1996 to optimize real-valued functions. It's also a simple population-based stochastic optimizer. It also has global convergence characteristics. And the name comes from that the evaluation here is now based on differences between the individuals. So that's the reason for the name differential evolution. And we will also show you why it's called like that in the following slides. We start with the initialization. The initialization is pretty similar to the genetic algorithm. One difference is here we have a minimum amount of population size. So we need at least 4 individuals to carry out the differential evolution, because otherwise it doesn't work. And then for the first phase you usually also have a random sampling method within the lower and upper bounds of the design variables, and this is your starting point. Afterwards you have now a mutation and recombination or crossover step here. With respect to mutation, we first choose a reference design, XA. So this reference design is chosen out of our population, so it's one individual out of it, and additionally we choose 3 individuals out of the population. That's also the reason why we need at least 4 individuals to carry out the differential evolution. And those are chosen randomly, so there is no evaluation taking place. Afterwards, the donor vector is defined as the weighted difference of these 3 randomly chosen individuals. So one of them is the start point, and then we build the difference vector out of the other 2s. And there's also the so-called mutation factor. So this is scaling the difference vector of those 2. Usually, so that's just, these algorithms are heuristic algorithms. So usually you choose a factor f, so the mutation factor between 0.5 and 1. After the mutation, the recombination takes place. So mutation and recombination in differential evolution are somehow connected, because the next step for recombination is you have a crossover constant, CR, which can be chosen, and then you compare. So this is a random selection process in the recombination. So you have a random number generator here, RND, and if the random number generator is smaller than the crossover constant, then you choose so this is one component of the donor vector, then you choose this component of the donor vector for the so-called trial vector U. But if the random number generator is greater than your chosen crossover constant, then you choose the component of your reference design variable vector, XA, for the trial vector. So that means with respect to this random number generator, it could happen that either the whole, so the trial vector is the same as the donor vector, but it could also happen that the trial vector is equivalent to the reference design, or of course some mixture of it. The crossover constant can be chosen between 0 and 1. And out of this, the trial vector is created for the whole population, UA. So you do that with all individuals of the population. Afterwards, there is an evaluation and selection process. So the reference design vectors XA of a certain iteration and the trial vectors that were built out of the donor vector and the randomly chosen designs are both evaluated and then compared to each other. And always those with the low objective function value or the better fitness are selected for the next generation k+1. So let's see 2 examples. So let's say we have one trial vector of the first reference design that's compared to the reference design vector, and since the trial vector has a low objective function value, it's chosen for the next iteration or the next population 2. And also the other way around. Let's say here we are on iteration 6 now, so it's the 6th iteration within the differential evolution algorithm, but now the new created trial vector has a higher objective function value than the reference design. Then we choose the reference design of iteration 4 for the next iteration 5. Lastly, we come to the particle swarm optimization. The particle swarm optimization was developed by James Kennedy in 1995, and it's inspired by the idea of simulating social behavior. And I think you can see that right away by looking at this animation. So let's wait until it starts again. So how it works is you have an initial swarm, and then there is a swarm behavior. So all individuals are acting with respect to the other individuals and themselves. And this is the basic idea of a particle swarm optimization. You can also see one difference by looking at the overview of the algorithm. So here is no recombination, no mutation, no evaluation or selection explicitly, but other terms as objective update or velocity update. However, James Kennedy stated that even though sometimes it's referred to as an own branch, so-called swarm algorithms, it shares conceptual similarities to evolutionary algorithms, and that's the reason why we categorize the particular swarm optimization also as an evolutionary algorithm. The initialization phase of a particular swarm optimization is also based on random sampling mostly, and it's randomly sampled within the feasible design space. However, each particle is now defined by 4 factors. So there is the position itself, so this is the design variable vector for each particle or individual, so it's xa. But on top we have a velocity for each particle, and also an individual best position, so this is more or less like a memory, so there the best position of each individual is saved, and on top also the individual of the best objective value. So within the whole swarm, so all design variable vectors, the best position is also one factor of each particle here. And for the initialization phase, those things are created randomly. Next, we come to the objective update. In the objective update, each particle is first evaluated. So here again, you see one basic operator of evolutionary algorithms. So at each position, the objective function or the fitness function value is evaluated, and then 2 things are carried out. First, the individual best position is updated. So here you see it again. What you do is you have the current position of your particle and you compare it with the latest best position of your particle, and if it's better, then this is the new best position. Otherwise, you just take the old best position again for the next iteration. And on top, we have the global best position, so out of all particles of the swarm. But the basic idea is the same, so you check the individual best position with the swarm best position, and if this individual best position is better, then it's a new best position of the whole swarm. Otherwise, you take the old best position here. The next step is the velocity update. For the velocity update, now all those 4 factors are combined. So this is the main ingredient. So this is inspired by bird swarm analogy. So what we do now is we calculate a new velocity for the next iteration by a linear combination of the current velocity of the individual best position and the swarm best position. And this is used to create the new velocity, which then is used for the next position. And these terms can be described by that the old velocity plus an additional weighting factor is some kind of inertia. We had that before for the conjugate gradient, for instance. Then there is this cognitive component. So here the individual best position compared to the current position is taken into account. And lastly, there's like a social component. So here the swarm's best position is taken into account. And all of this as a linear combination adds up to the new velocity. And you can see it also here on the right side. So we have the inertia term of the current position. And we have the cognitive component. So this is the best position of the individual so far. And we have also social components. So this is the position of the best swarm position. Out of this, the new velocity is created. And the new velocity plus the current position is used to create the position of the next iteration, which is here then. And you see that you have different weighting factors as well. So you have the weighting factor for the inertia, and you also have the weighting or the random uniform variables for the cognitive and the social component as well. And this is done for each individual to create a new particle position. And now to conclude, we presented 3 types of evolutionary algorithms. We had the genetic algorithm, we had the differential evolution algorithm, and particle swarm optimization. They are all based on principles of biological evolution and genetics somehow, But like I said, particular swarm optimization is a bit different there, but they are all based on a population of designs that are iteratively modified. And we have always new generations which are created by some heuristics. And more importantly, also some general remarks that hold for all evolutionary algorithms. So why do we use evolutionary algorithms? Like I mentioned in the beginning, it's a zero-order based method. So this can be beneficial because you don't need gradients for that. And sometimes it's hard to calculate those gradients. So also for black box functions, those evolutionary algorithms in particular are a good choice. They are in general very fast in approaching the vicinity of an optimum. And they have on top this global convergence characteristic. But remember, this doesn't mean that you always find the global optimum. But in contrast to local optimization algorithms that are gradient based, you have a higher chance of finding a global optimum. One disadvantage is, however, that they have problems in finding the exact position. So what you do sometimes, and it's also implemented, for instance, in MATLAB, is that after evolutionary algorithm, you can still use a local optimizer, gradient-based optimization, to find the exact position of your optimum. This is often done. Evolutionary algorithms in general are suited for non-convex design spaces because of the global convergence characteristic. For noisy problems, so remember, for noisy problems you also have difficulties with calculating the gradients, for instance. You don't have this problem here. Also, discontinuous design spaces are not a problem, and especially the genetic algorithm is suited for discrete optimization problems where the design variables can only take values like 1, 2, 3, and so on. But this doesn't hold for all evolutionary algorithms. In general, compared to gradient methods, you need more function evaluations. So it's more expensive, but sometimes you don't have a choice and you need to pay this price, let's say, because other algorithms are not suitable. There is always a trade-off when you use an evolutionary algorithm, because you have, on top of the specific parameters as the crossover constant and so on in the differential evolution, you have always the choice on choosing how big your population is and how many generations you want to carry it out. And this has an effect on the number of function evaluations and also the convergence characteristics. In general, all evolutionary algorithms can be applied to unconstrained and constrained problems. There are different ways of handling constraints. There are direct methods where you just eliminating the infeasible individuals or you repair them. So this means, let's say, for the selection process, you can only take individuals that are feasible, or you just put them back in the feasible region. There are also methods that are using some kind of penalty barrier function or also augmented Lagrange implementations. So both is possible, so it's suited for constrained and unconstrained problems. There are different methods on handling those constraints here. This brings us to the summary. Lecture 5 and Lecture 6 contained a lot of different algorithms, and I know that might be a bit overwhelming in the first place, so we now try to summarize all of it, and maybe that helps for you understanding. So in Lecture 5 we started with the basic steepest descent algorithm. And the steepest descent algorithm is a first order method. First order refers to the information that is used. So in first order methods, we are just using gradient information. And the search direction of the steepest descent is the negative of the gradient. Within the steepest descent, we have an additional 1D optimization where what we call the line search. Also in the line search, we define the step size in the direction of the search direction. So how long do we follow the proposed search direction? There are 3 parts of it. So there's bracketing. In bracketing, we try to cover the area where the optimum is assumed. In sectioning, we try to reduce this area further. And then we had the polynomial approximation. So here, approximation of the objective function is made, and this is used to define the approximated position here for the step size. We can either do it with zero order information, so here we use 3 points for it, or we can also do it with first order information, so here we use 2 points, and for 1 point there is additional derivative information. However, for the basic steepest descent, there are several problems. One problem we mentioned in lecture 5 was zigzagging. And so for zigzagging, it happens in a flat region of the objective function, and then the number of iterations gets bigger and bigger. One way of getting rid of it is, for instance, to use conjugate gradient. So here we added an inertia term to the search direction of the negative gradient, which helps to reduce this the number of iterations. Another way of reduce the number of iterations is to use more or higher order information. Second order information has curvature information, so here we use the Hessian on top. So the modified Newton's method uses gradient information and the Hessian to calculate the search direction. However, second order information is more expensive, so we also showed methods to approximate second order information. So these were the quasi-Newton's method, the BFGS for instance, where second order information is built out of first order information. After this, the last part of lecture 5 was concerned already with constraint problems. However, barrier and penalty methods, what they do is they transform the constraint problem. So we have an objective function, but we also might have inequality or equality constraints, but we put that all together into the meta-objective function with barrier or penalty constants. And by doing this, we can still apply methods for unconstrained problems to those. And finally, we also had a dual method. So in dual methods, we use both, so penalty or barrier constants, and also Lagrange multipliers. And this was lecture 5. Then we proceeded with lecture 6. It was mostly concerned with what we categorize as Lagrange methods. So we had sequential linear programming, where the real nonlinear problem is linearized and then solved in an iterative manner. And then we have the sequential quadratic programming, either with approximated second order information, so quasi-Newton, so it's first order, or with real second order information. Sequential quadratic programming is one of the most powerful methods in optimization, as long as you can access the derivative informations or second order informations. And lastly, we had evolutionary algorithms. Important is here that they can be applied to unconstrained or constrained problems. Actually, there are also some evolutionary algorithms that use Lagrange multipliers, but mostly they are primal methods. That means they are just acting on the primer design space, so the design variables X itself and nothing else. We had here methods as the genetic algorithm, the differential evolution, or the particle swarm optimization. And with this last method, the lecture 6 is over. Thank you very much for your attention, and see you in the recitation.